This experiment was focused on studying the laws of elastic and inelastic collisions, and it was conducted by Sarah Borovic, Jordan McLean, and Anela Poljak. The primary objective of this lab is to help students uncover the principles behind the law of conservation of momentum through its applications in inelastic and elastic collisions. Students will also delve into the propositions of the conservation of energy through elastic collisions. The chief purpose of this lab was to discover how momentum is conserved for inelastic collisions by altering the mass of the cart. We were able to confirm that the law of conservation of momentum applied by measuring the initial momentum and final momentum for the changed masses. For elastic collisions, the energy was conserved when altering the mass, confirming the law of conservation of both momentum and energy. Measuring the initial and final momentums for the changed masses helped validate our predictions.
In this experiment, momentum, conservation of momentum and energy, along with elastic and inelastic collisions were the main ideas we focused on. For both collisions, momentum is conserved, and for elastic collisions, energy is also conserved. An inelastic collision is a collision in which momentum is conserved while kinetic energy is not conserved in the collision, while an elastic collision is a collision in which the momentum and energy are conserved in the collision. For activity 1, conservation of momentum was understood to be at work. We utilized the idea of conservation of momentum to allow us to state that the sum of the initial momentums for the first and second cart before the collision is equal to the sum of the masses of the two carts multiplied by the final velocity of the two carts as they are attached after the collision. For activity 2, which focused on elastic collision, we utilized the following calculations to study how momentum and energy are conserved for elastic collisions. The initial momentum of the system before the collision can be set equal to the sum of the individual momentums for each of the carts. The individual velocity for the second cart is set to 0 because the second cart was stationary prior to the collision. This results in the initial momentum of the second cart being 0. Therefore, the initial momentum of the system is equal to the mass of cart 1 multiplied by the initial velocity of cart 1 before the collision. The final momentum of the system after the collision can be set equal to the individual momentums for each of the carts. Applying the principle of conservation of momentum, we are able to set the initial momentum of the system equal to the final momentum of the system. The same principles used in deriving the equation for the conservation of momentum allowed us to derive the equation for the conservation of energy. Utilizing the two equations just derived that describe the conservation of momentum and energy, we divide the two equations. The result allows us to conclude that the sum of the initial velocity of cart 1 before the collision and the final velocity of cart 1 after the collision is equal to the final velocity of cart 2 after the collision. The final velocity for cart 2 after the collision in the equation for the conservation of momentum is substituted by the equation just derived. After simplifying the equation, we are able to determine that the final velocity of cart 1 after the collision is equal to the difference between the mass of cart 1 and the mass of cart 2 divided by the sum of the masses of the carts, all multiplied by the initial velocity of cart 1 before the collision. Once again, using the equation derived from dividing the equations for the conservation of momentum and energy, we substitute the initial velocity of cart 1 before the collision with the equation just obtained. Once this equation has been simplified, we are able to conclude that the ratio between the final velocity of cart 2 after the collision and the initial velocity of cart 1 is equal to 2 times the mass of cart 1 divided by the sum of the masses of the carts.
In this lab, we used several different apparatuses or materials. Our first material that we used was a long track. On that track, we had two carts. For those carts, we utilized various cart masses placed on top, as you can see in the bottom two images. Additionally, we used the Pasco motion sensor, the Pasco program, and a laptop, and a scale to measure our carts and record those masses. Our methods were divided into two activities. The first activity was inelastic collisions. Our first step was to set up a track and a motion sensor on one end of the track. Sequentially, we weighed each of the two carts we used and recorded their masses in Excel. Add the two carts to the track with the two sides having Velcro facing each other, allowing for the carts to attach after the collision. Once the carts were on the track, we standardized the distance from the force sensor to the second cart and kept it consistent throughout the experiment. After this was done, we set up Pasco on the laptop in order to record our velocity versus time graph throughout the experiment. Our first trial was done by pushing the first cart into the second cart. This first trial had no mass on top of the first cart. After the first trial, we added 10 different masses for each of the trials to cart 1 for each trial respectively. The second cart did not have any mass added on it for any of the trials. Once you've added your mass to the cart, press record on Pasco and record the collision of the first cart into the second cart. Pasco recorded the velocity at the top and bottom of the peak, with the top point representing the initial velocity before the collision and the bottom point representing the velocity after the collision. Complete 12 trials and record the data in Excel. Activity 2 of this lab consisted of an elastic collision. In Activity 2, we set up a track and 2 motion sensors on both ends of the track. We added 2 carts from the previous activity to the track with magnetic ends of the carts facing each other. Note that in Activity 1 of the lab, we had the Velcro sides facing each other. This time, we have magnetic ends. We set up Pasco to record a velocity versus time graph. After the first trial, add the same masses for each trial respectively in the same order as Activity 1. Allow the mass of cart 2 to remain constant. While Pasco is recording the collision, push the first cart into the second cart and record the initial and final velocities of the 2 carts. Complete 12 trials and record the data in Excel.
In this experiment, we collected our data in this Excel file. Before the experiment began, we took the mass of the first cart and the second cart that we were using and recorded that in our Excel document. The first mass of the cart was changing throughout the experiment over our 12 trials. We added incremental weights for every single trial as described previously. The initial velocity before the collision for the first cart was recorded from Pasco. The mass of the second cart remained constant throughout the entire experiment. The initial velocity of the second cart was recorded and placed as 0 because the cart was stationary before the collision in the experiment. The second cart was also positioned at 60 centimeters throughout the entire experiment to standardize that aspect of our activity. The third velocity that we have listed here was collected from Pasco after the collision had occurred. The M3 listed here is a sum of the first and the second cart used after the collision. The initial momentum before the collision was calculated by taking the sum of the mass of the first cart multiplied by the initial velocity of that cart before the collision with the product of the mass of the second cart multiplied by the velocity of the second cart before the collision. The final momentum after the collision was calculated by multiplying the sum of the masses of the 2 carts by the velocity of the 2 carts after the collision. As we can see here, the values are similar, but we confirm that this is a relationship depicting the law of conservation of momentum based on the slope of the line, which is close to 1. In Activity 2, we recorded the masses of the first cart, which changed incrementally as they did in Activity 1. We recorded the velocity before the collision from Pasco and recorded the mass of the second cart, which remained constant throughout the experiment. The velocity of the second cart after the collision was also recorded from Pasco. Based on the calculations done in the theory section of our experiment, we concluded that to confirm the law of the conservation of momentum and the conservation of energy, the ratio between the final velocity of the second cart after the collision over the initial velocity of the first cart before the collision, that should be equal to 2 times the mass of the first cart over the sum of the masses of the 2 carts. Based on the data that we collected and the graph that we were able to create using this data, we can confirm that the law of conservation of energy and momentum were applicable in this experiment. For this experiment, the results for Activity 1 were that the slope of the first graph was 0.9217 and the r-squared value was 0.996. The results for Activity 2 were that the slope of the graph was 1.0266 and the r-squared value was 0.8982.
In conclusion, we were able to experimentally determine the validity of the law of conservation of momentum through inelastic collisions and the laws of conservation of energy and momentum through elastic collisions. For the inelastic collisions, we found that altering the mass of the initial cart changed the final velocity of both carts together, and the change in velocity linearly followed the change in mass, indicating that the overall momentum was conserved. Since the slope for this graph was 0.9217, we can conclude that the relationship between the initial and final momentum was proportional. Due to the r-squared value, we can confirm that our data was precise. Sources of error include the systematic error, which can be found in the y-intercept. For the elastic collisions, we determined that the change in velocity linearly followed the change in mass, indicating that the overall energy and momentum were both conserved. Since the slope for this graph was 1.0266, we can conclude that the relationship between the x and y intercepts of the graph for the elastic collision was proportional. Due to the r-squared value, we cannot confirm that our data was precise. Sources of error include the systematic error, which can be found in the y-intercept. Interestingly enough, the concept of momentum was originally introduced by a French man named René Descartes. He discovered, experimentally, that momentum is simply the product of the mass and velocity of the moving object of interest. Isaac Newton then expounded upon these discoveries and came up with his third law, the law of conservation of momentum, which states that for a force applied by object A on object B exerts back an equal force and magnitude, but opposite in direction, on object A. Descartes is more widely known for making an important connection between geometry and algebra, but it was interesting to see how he had such a vital role in both the areas of physics and mathematics. We would like to thank Dr. Bola for his instruction throughout the semester and our TAs, Oscar and Chris, for their assistance.